HSC physics, the photoelectric effect. I'm going to be going through some problems that are typical in the HSC on the photoelectric effect, typically calculations that students sometimes find a bit challenging. So I'll try and demystify those as best I can. So I'll start off with this typical problem here. Suppose you need to calculate the energy. So these aren't from any particular paper, they're just questions that I've come across over the years, and they seem to pop up every now and then. So calculate the energy of a photon if its wavelength is 500 nanometers. So that's our question there. The way to tackle this is to first look at what this question is, what main concept the question's all about. So this involves typically the photoelectric effect. This type of question is typically asked in short answer questions for the photoelectric effect, sometimes multiple choice, but you typically see these in the photoelectric effect. So what you need, so energy, so we know, looking at the HSC physics formula sheet, the energy of a photon is given by the Planck relation HF. E equals HF. E is the energy measured in joules. H is Planck's constant, that's on the HSC data sheet, 6.626 times 10 to the minus 34 joule seconds. And F is the frequency of the photon measured in hertz. So that's our starting point there. Now we need to calculate the energy given a wavelength of 500 nanometers. So that's a hint as to what we need to do to this equation here. We're not given wavelength, however, we do know that F, use a different color. We can rewrite this in terms of the following. So just aside here, as an aside, we can relate the speed of light, c, to F via c equals F lambda. Instead of v, we'll put c because light travels at the speed of light. C is the speed of light, 300 million meters per second. And so that's how we can calculate F, in other words, by rearranging the formula. F is equal to c over lambda. C is the speed of light, so let's plug that in. 3 times 10 to the 8 divided by lambda, the wavelength. We have to be careful here. 500 nanometers. A nanometer is 10 to the minus 9 meters. So 500 times 10 to the minus 9, just to keep track of units. Punching that into your calculator, you would get an answer of 6 times 10 to the 14 hertz. So that's the frequency there. That's not the end of the story. We need to plug it back into E equals HF. So H is Planck's constant, 6.626 times 10 to the minus 34. F is what we just calculated now, 6 times 10 to the 14. Punching that into your calculator, you get an answer of 3.98 times 10 to the minus 19 joules. So this is typically a 2 marker, 1 mark for the working out, 1 mark for the answer. So that's your answer there. And it makes sense, sanity check, 10 to the minus 19, because it's a single photon, okay? It's not going to have a massive amount of energy. But collectively, lots of photons, they'll have a decent amount of energy. The next type of question I find students sometimes struggle with is that involving stopping voltage. Let's look at that. Suppose we're given the work function for zinc to be 4.3 electron volts. And we need to work out the stopping voltage for the photoelectrons apologies, the stopping voltage for the photoelectrons is, let's suppose, 1.5 volts. And we need to determine the frequency of incident light. Here's how we would tackle this question. You would need to use, so the first thing that comes to mind is the photoelectric effect. That's what it's all about, this question, because it involves the work function and things like stopping voltage. You would need to go to the HSC physics formula sheet and find this formula here for the photoelectric effect. So the maximum kinetic energy is equal to HF, the energy of each photon, minus the work function phi. Now, this isn't the end of the story, but we know what the work function phi is. It's in the question for zinc. But we're given stopping voltage. We don't know what the frequency is. We know what Planck's constant is, but we don't know, and we also don't know the maximum kinetic energy. We need to go back to year 11, module 4, electricity and magnetism. We know that from the law of conservation of energy, the change in kinetic energy is equal to minus the change in potential energy, and that's just equal to the work done, okay, on a particle. So in this case, the photons, the electrons, apologies. We know that so this relation here, the change in potential energy, also known as the electric potential, is related to voltage as follows. The potential difference is equal to the change in electric potential between 2 points per unit charge. So suppose we have initial electric potential for a charge Q at some point here, and the final electric potential for some charge Q, for the same charge Q at some later point. It's related, so the voltage V, otherwise known as the potential difference, is related to electric potential as follows. So we know what the voltage is, V. We know what Q is, it's the charge of the electrons in this case, so we can find K, the kinetic energy in this case. So delta U is equal to Q V. I'm going to get rid of the deltas for now. U is equal to QV, and that's equal to K. So we can plug in this value for K in the formula above. So we get this. So K max is equal to QV, and that's equal to HF minus phi. We know what Q is, charge of the electron, that's on the data sheet. We know what V is, the stopping voltage. Let's put a sub S here, stopping voltage. We know what H is, Planck's constant. We need to work out F, and we know what phi is. So there's only one unknown. We can easily do this. It's best to now convert all of the values we're given in terms of joules. So Q, that's the charge of the electron, minus 1.602 times 10 to the minus 19. Let's get rid of the minus for now, because frequency is a positive number. Stopping voltage is 1.5 volts times 1.5. That's equal to Planck's constant, 6.626 times 10 to the minus 34 times F, the unknown, minus the work function phi. So phi is 4.3. To convert that into joules, you multiply by 1.6 times 10 to the minus 19. Just look at the data sheet. And all you have to do now is use algebra. I'm going to skip some steps to find F. Doing the maths, you'll get this number, 1.40 times 10 to the 15 hertz. So that's how you tackle this question. Well, it involves a couple of steps, but it's starting off with the photoelectric equation and knowing that kinetic energy is related to potential energy through this relation here, law of conservation of energy. And then delta U, the electric potential, is related to the voltage as follows through this formula here. And you rearrange for U to find U that is QV, and that's equal to K, and you plug it back into the formula at the top here and rearrange for F. So these are typical photoelectric effect HSC questions.